very easy. Given a non-negative integer n, find its factorial, n factorial, this notation. So we are familiar with this notation, right? And so it's a simple problem from the textbook. Very simple. And usually we do not rely on recursion, right? Solving a simple problem like this, why we need to use recursion, right? We don't need. But here, as an example to get a good understanding, we need it. We like to view it from the recursion point of view. Method one, iterative way. We just write a for loop. We can find its value easily. And let's start from the definition of recursion. We know this is the definition. The product of these n consecutive positive integers from 1 through n. And here, remember, in our given question, we say non-negative integer n. That means n, it is allowed n to be 0. This case is included. But n what is the 0 factorial? If you look at from this definition part, it's not easy to guess what is the value for the 0 factorial. Some people, if they use their intuition, they may guess 0 factorial should be 0, right? Yes, by intuition, because 0 do multiplication. How do you? We know 0 multiply anything must be 0. Then there is a natural way to guess the value by the intuition, 0. But here our assumption, this is assumption. The assumption tells us it's not 0. It's 1. But how to understand? How can you see it? How do you see it? 0 factorial equals 1. Although you say people make assumption, but assumption, when you make assumption, you cannot cause any contradiction, right? If you make assumption, but later your assumption contradicts your logical results you derived later, then your assumption is wrong. You cannot make a wrong assumption, right? So you need to make sure this assumption is correct. This one is correct. No contradiction. We will see that. Later we will see this assumption is correct. No contradiction. Okay, So that's the reason we can make this 0 factorial equals 1 assumption. Okay, compatible with all our logical reasoning. Okay, all right. Here, based on a definition, people can easily, so we will answer this question later. Okay, Here, still, we need some more information. We do not have sufficient information at this point. We need to collect a little more information. All right. Implementation is straightforward. A for loop, a simple for loop. So here I do not need to write it out explicitly. But method 2, recursive. This time, let us consider the recursive way. All right. So the general idea, so when we do the recursion, the general idea is like this. general problem approach. Yeah. Divide and conquer. Yeah. It's a commonly used method in problem solving, divide and conquer. Yeah. So this one is a big topic, divide and conquer. You know, this in problem solving, this is a big topic. Yeah. And in our module 2, not module 2, module 4, we will cover divide and conquer, the whole module. Yeah, we will study divide and conquer approach. Okay, yeah. But here we already use it. Now, when we do our recursion, we need to take this divide and conquer approach. Yeah. All right. First, the problem is easier when the size is smaller. So when we start solving a given computing problem, we start from the cases with very small sizes, because that's very easy. Yeah. Yeah. All right. So after that, when you work on a problem of the current size, yep, because eventually you need to work on any given size, right? Problem, any given size. Yeah. So we treat it as current problem size. Assume that a problem of a smaller size has been solved. So here, this is assumption. Yeah. That's what I talked about in the previous slide. That assumption, we can assume that. Yeah. Why we can assume that? It's not baseless. We cannot make baseless assumption, right? Yeah. That assumption has a solid base. This is its base. Okay? So that's why we call it base cases. These smaller problem sizes, we call it base cases. Yeah. Could be multiple cases. Sometimes one base case is enough. Sometimes we need more than one base cases. Yeah, base cases. So that's the reason we can make assumption like this. Okay, all right. Then, but there is a gap. The current problem size and the previous problem size smaller, current problem size larger, and how to fix the gap between these two, the same problem with two different problem sizes. There is some gap. We need to fix it. Okay, yeah. That fixing formula, the formula to fix it, that is the recurrence relation. If we can discover a recurrence formula or equation, then we can fix the gap between two different problem sizes. That's the basic idea for the recursive method algorithm. Yeah. All right. So based on this general description, so this is general for all recursion type solutions. Yeah, all. Yeah. And the problem size larger, smaller, that corresponds to divide and conquer. Yeah. You divide. When you divide the given problem, you make it smaller, right? You make the problem sizes smaller. Then you conquer. Conquer, here we use recursion to conquer. That's legal, yeah, because the recursion is supported by high-level programming language. So it can be implemented. So it's legal. Yeah. So we conquer that. All right. Then you need to do the step number 3, you need to fix the gap. Okay? So then you complete that divide and conquer, the whole method here. Okay? Yeah, that's the divide and conquer understanding of recursion. Okay, yeah. Now, let's work on this factorial problem. Work, especially mainly that recursion part. Yeah. All right, so when we start from the definition. This is the formal definition of the factorial. Yeah. The left-hand side n factorial, let's assume we do not know the answer. Okay, yeah, that n factorial, that big number, we do not know its answer. Yeah. So our goal, we want to find its answer. Okay, in that way, we introduce a representation for it, a function called f of n, capital F function, with problem size n. Okay, so the left-hand side, we use f of n to represent n factorial, its value. Yeah. All right. With this representation, now we try to look at the right-hand side expression. Right-hand side, this product of n consecutive non-negative, actually positive. Here there is no reason, no zero value involved, so we can call n positive integers. All right. Then we apply divide and conquer. Yes. Here we need to use that divide and conquer view. How to divide? The divide way is a special way. We just chop down the last operand number. Your product. You have n operands in your product, right? There are n operands in the current n factorial product. But now we chop off the last operand. Why we chop off the last operand? We want to reduce the problem size. The reason, so here, I mentioned this idea before. So the idea, so let me recall, we used, that's the problem size reduction. Problem size reduction way. Here, we reduce the problem size. But how do you reduce? The question, how do you reduce the problem size, right? Here we use a special way to reduce the size by 1. Only the size is 1 smaller than the current problem size. Okay, so we chop off only 1 operand from the product. Okay, one size reduction. So it is one of the special cases. One of the cases when we do divide and conquer. Later we will have many different cases. Here is the simplest case. One size reduction case. Okay, all right. After that reduction, how to represent this part? We have the definition, n factorial, capital F of n. Can we use this notation, this function, to represent the product at the left-hand side of the vertical bar we use to chop down the last operand? That is capital F of n minus 1. Capital F of n minus 1. Okay? So its expressions simple. Yeah. Next, then the original formula can be represented in the simple way. Capital F of n equals f of n minus 1 times n. That's the recurrence relation. This recurrence relation is used to fix the gap between two problem sizes, right? One problem size n, another problem size n minus 1, and their relationship, this whole equation is the relationship, okay? Yeah, so with this recurrence relation, we can implement it easily, right? Yeah, so, but here in our representation, we require that n greater than 0. Yeah. Otherwise, we may have trouble, right? In this representation, we may have trouble. So n must be greater than 0. Okay, all right. Yeah. The question, how to see that 0 factorial equals 1? Now we need to answer this question. Yeah. Because without any reasonable explanation, you cannot make assumption like this. Because you may have some contradiction if you make arbitrary assumption. Yeah. You have to find some good reason to support your assumption. Here, we can do it. Here, let us write our recurrence relation in this equivalent formula. Yeah. F of n minus 1 equals f of n over n. That's equivalent from our recurrence relation, right? Yeah. And from this formula, yeah, if we plug in n equals 1, can we make n equals 1? We plug in, so we have left-hand side, f of 1 minus 1, that's 0. F of 0 equals the right-hand side, f of n over 1. F of 1, yeah, f of 1, we know 1 factorial, right? 1 factorial equals 1. 1 over 1 equals 1. So that means f of 0, that is a 0 factorial, right? Yeah, because based on our, definition, if we do extension, we may need to do extension a little bit. That corresponds to 0 factorial, okay? F of 0 corresponds to 0 factorial. So this tells us, yeah, this equivalent formula, equivalent to the original recurrence relation, that results in this 0 factorial equals 1. Yeah. That's the reason if we make assumption like this, no contradiction. It's compatible with our recurrence relation. Yeah. So that's the reason we can make this assumption. Okay. All right. Yeah. So here, the conclusion, the final conclusion. It is an interesting way to solve the problem. Yeah. Why I say this way? Because to calculate n factorial, we don't need a recursion, right? Yeah. Nobody needs recursion to calculate n factorial. But for this simple example, we see it's a different way from the iterative method implementation. Yeah. But it's an interesting way. Interesting because the idea, problem size reduction, and this idea probably can help us to solve many relatively hard problems. That's the value we like to have. Yeah. For future, yeah. So let's say the purpose, main purpose, yeah, for solving future, relatively hard, because, how to understand hard problems, right? For different people, the understanding could be different. Let's say relatively hard problem. That's the main value of this method, okay? That's the importance of this method, All right, so here you see some introduction. So here I use this example as introduction for the recursion, okay? Recursive method. And then later, we will try to expand to cover several different cases, commonly used cases in recursion.